Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off several weeks back when we had derived several of the parameters of this equivalent circuit of a single phase induction motor. So since it has been a few weeks, I will do this one lecture will be a bit of a recap of everything we've done and also a little bit of a roadmap of what we're going to do next, right? So as I said, this is the equivalent circuit of a single phase induction motor, right? Or you could even look at it as the single phase equivalent circuit of even a multi-phase induction motor, like a three-phase induction motor, because we can represent any motor in the per phase form with such an equivalent circuit. And of course, this equivalent circuit will actually represent this induction motor. So this is, of course, as I said, I've shown this page before. This is just a page which I found by doing a Google search of single phase induction motor. And this is a single phase induction motor, right? So this, as you can see, there is the stator which is mounted on a foundation. So these are the mounts. This stator will receive an ACC input, and within this stator is mounted the rotor. And here we have considered a special case of a squirrel cage induction motor where the rotor consists of bars that have been short circuited on both ends, right? We can also think of a wound rotor induction motor where the rotor consists of actual windings that are wound on the rotor, just like it is wound on the stator, and the terminals are brought out in the form of a slip ring, right? That is also possible, but for now we can start with a squirrel cage induction motor. So this single phase induction motor can be represented by this particular equivalent circuit. Now there is a bit of a complication in the sense that a single phase induction motor is not self-starting by nature, right? And we'll talk about that through simulations. But in order to make it self-starting, a single phase induction motor usually has an auxiliary winding, right? So for example, this is the main winding, which is the stator winding, and this is an auxiliary winding, and this auxiliary winding is what we will add later, right? So currently what we are looking at is this main winding and this squirrel cage rotor. That's all we are looking at. We will add this a little later. So if we look at this, we are applying the single phase supply to this main winding, right? And this main winding is going to produce a magnetic field in this air gap, which is going to induce an EMF in the rotor, thereby causing currents to flow. And these currents in turn will produce another flux, and the interaction between the stator flux and the rotor flux will cause this rotor to rotate, right? That is the concept of an induction motor. Now let's come back here. So in this single phase equivalent circuit, we had said that this is the supply and everything else is this main winding. So everything after this column is this main winding L1, right? We are trying to break it up and trying to produce a complete equivalent circuit that we can represent this motor with. So for example, we are saying, first we said that this entire stator can be represented as just one inductance, right? And which is how it has been done here as well, right? And we had also said that due to the process of induction, there will be a rotor inductance which will be coupled to the stator inductance, and this rotor inductance will feed this rotor resistance, right? Inductance and resistance. Now we had also said that because of the nature of the motor, that is the nature of how the system is, because it's a rotating motor, the rotor will have a frequency which is different from that of the AC supply, right? So eventually we had said that we can simplify it such that we can bring both circuits, that is the rotor circuit and the stator circuit, to one frequency, pseudo frequency, by dividing this slip term throughout the rotor circuit, right? And once we do that, we can merge these two circuits by creating them as equivalent parameters. So we have referred all the rotor parameters to the stator. And as a result, we have this one single equivalent circuit which is connected together, which represents the entire rotor. So for example, this consists of a stator winding resistance, right? That is here the stator resistance. LLS is the leakage reactance of the stator, because remember, all the flux that is produced by the stator will not be in the air gap and will not associate with the rotor. Some of it will leak into the air and will not couple with the rotor. This LLS represents that. RC is the core loss resistance of this, that represents the core loss resistance. So for example, when there is a magnetic field, there will be a core loss component in the magnetic system. So for example, in the stator, there will be hysteresis losses and eddy current losses. These are there when any magnetic field is produced. This RC represents that. LM is the magnetizing inductance. So this LM represents the actual inductance, which will produce a flux that links with the rotor in the air gap. So this is the actual working flux. And this working flux is produced by this magnetizing inductance. And then finally there is LR, which is the LR dash rather, which is the referred rotor inductance. And there is RR dash, which is the referred rotor resistance. And we had talked about this also, how we can refer the rotor parameters to the stator. So now that we had this, the next question is, how do we estimate all these parameters? So as I already said, we've all done this during our undergraduate studies. We've done what is called as the no-load test and the blocked rotor test. So if you have a motor, a physical motor in the laboratory, one option to determine the actual rotor parameters is by using what is called as a no-load test and a blocked rotor test. And this is very similar to an open circuit test and a short circuit test that is performed on a transformer. So in a no-load test, we apply the rated voltage to the stator. So if the motor is a 240 volt 50 Hz motor, we would apply 240 volts AC supply to the stator. That is the rated voltage. And we would leave the rotor in the no-load connection. So for example, we assume that this motor is therefore has no load. Of course, it has some basic load because the rotor itself is a base load. But if we neglect even the rotor inertia, then in that case, we can neglect this entire resistance and this rotor circuit is considered to be open circuited. Because at no load, the speed is going to be very close to the synchronous speed and therefore slip S is almost close to 0. As a result, this rotor circuit is considered to be open circuited. Using that, we can estimate the leakage inductance and the core loss component. Because all the losses in the motor at no load is usually the core loss component. And we can also estimate the current that is drawn by measuring the current that is drawn by this motor, we can estimate the magnetizing inductance. Usually we do not estimate the stator resistance or the leakage reactance of the rotor because since the current is negligible at no load, these drops across these will be negligible. Then in the stator test, and therefore with this we can estimate, as I said, we can estimate the rotor core loss component and we can also estimate the magnetizing inductance. So the next thing is the blocked rotor test. In the blocked rotor test, we apply a very low voltage such that the stator is drawing the rated current corresponding to the maximum rated power. So if this motor is, let's say, a 240 volts 5 kilowatt motor, then in that case we calculate the rated current at 5 kilowatt, which is the maximum rated capacity of the motor, and we increase this, we block the rotor, so we don't let the rotor move, right? We physically block the rotor and we increase the voltage such that this rated current is flowing through. And this is very similar to the short circuit test and transformer, where we short circuit the secondary and we apply a very low voltage to the primary until a rated current flows in the primary of the transformer. So by blocking the rotor, we are fixing S to 1. And since S is 1, this impedance of this rotor branch is very low and resembles almost a short circuit, similar to a short circuit test of a transformer. Now, in the blocked rotor test, since a rated current is flowing, now the losses in the transformer will be mainly due to the ohmic losses, which is due to the stator resistance and the rotor resistance. The loss due to the core loss is going to be very low because since we are applying a very low voltage, the magnetic field is extremely weak. So therefore, the current drawn by the magnetizing inductance and the power that is absorbed by this core loss component resistor is going to be negligible. So it's mainly this parallel branch is considered to be open circuited, and we have just this one series branch. And therefore we can calculate the stator resistance, and we can also estimate the leakage impedance. And also all these, that is the inductance of the rotor and the resistance of the rotor. So using the no load test and the block rotor test, we can calculate all the parameters of this equivalent circuit. And even if we don't perform a no load test or a block rotor test, we can make assumptions that are quite reasonable, and which will result in a very realistic model of a rotor. So now the question is, this is where we had reached in the previous lecture. So the question is, what are we going to do with it? Now that we have this equivalent circuit, we can now start writing the equations of this system, and we can now solve this to create a dynamic model of a single phase induction motor, right? So we have done this for a transformer, and we have also, or rather I have probably have done this in one of the courses for a transformer. But at the same time, this can also be done for any system. In order to simulate a system, you need the dynamical equations of the system. And since we now have all these parameters, we can now write equations for the flux linkages in the stator and also the rotor, and also calculate things like torque and therefore the speed. We will have to make assumptions of course, the inertia of the rotor and also inertia of any load that is connected to the system. But these details will come very soon. So in the next lecture, we are going to use this equivalent circuit, and we are going to start writing Python code such that we can simulate the model of simulate an induction motor using this equivalent circuit, right? That's what we're going to do. So this is just a recap. If you're not sure about what all this was, please do watch all the previous videos where I had discussed how we start with two separate circuits, we simplify the rotor circuit, we then divide by S to make it frequency independent, and then we use the turns ratio, that is K, to merge these two circuits to produce a single circuit. So these have been described over the past several videos. If you're not sure, or if you would like to know more, please do watch those. In the next lecture, we will start with actual simulations. So as before, if you have any doubts, please do either send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week. Thank you so much for watching, and see you soon. Goodbye for now.